You know, every time you flip on a light switch, you're tapping into this massive, incredibly complex system. You just trust it's going to work. But what if I told you the very thing that keeps that system stable, this invisible force, is quietly disappearing as we switch to renewable energy? In this explainer, we're going to dig into that exact challenge and figure out what it's going to take to secure the future of our power grid. So, here's how we're going to break it down in this briefing. First, we'll look at the invisible flywheel that's kept our grid humming for 100 years. Then, we'll get into why that stability is now at risk. After that, we'll explore the cool new technologies that are engineering a solution. And finally, we'll lay out a really clear action plan for building a grid that's truly resilient. All right, let's start with the basics. For over a century, a really simple principle of physics has been the grid's silent guardian, its unsung hero. So what is this hidden force, right? It's something that was just so abundant in our old power grid that honestly, we all just took it for granted. But its absence? Well, its absence is creating a massive engineering challenge for us today. The whole story really starts with grid frequency. The best way to think about it is like the grid's heartbeat. Here in the US, it's supposed to beat at a super steady 60 hertz. As long as the amount of power being generated perfectly matches the amount being used, that heartbeat is stable. But what happens if a huge power plant suddenly trips offline? Well, the frequency starts to drop, and that's a big warning sign that the system is in trouble. And that brings us to this core concept, grid inertia. The flywheel analogy on this slide, it's the perfect way to get it. Just picture hundreds of enormous, heavy turbines in our traditional power plants, coal, gas, nuclear, all spinning together in perfect sync. All that rotational energy, that kinetic energy, acts like a colossal, invisible flywheel for the whole grid. It's this physical momentum that works like a shock absorber, naturally pushing back against any sudden changes. And here is exactly why that's so crucial. Let's say a big 1,000 megawatt power plant suddenly goes down. Instantly, the kinetic energy stored in all those other spinning generators gets released to cover that gap. Now, it doesn't solve the problem for good, but what it does is slow down the drop in frequency. And that buys the system operators a few precious, absolutely critical seconds to get reserve power online and stop a catastrophic failure. So here's the key takeaway. This natural physical stability we've relied on, it's basically a side effect of old technology. As we modernize and switch to new energy sources, we're accidentally creating a brand new and very serious risk, a stability deficit. And here's the challenge in a nutshell. Solar panels and wind turbines are amazing, right? But they connect to the grid using power inverters. They don't have any of those massive spinning parts that are physically locked to the grid's frequency. So every time we retire an old coal or gas plant and replace it with solar or wind, we are literally removing a piece of that giant stabilizing flywheel. This table just lays out the consequences in black and white. It's a night and day difference. A traditional high inertia grid is stable, predictable. A modern low inertia grid is, well, it's twitchy, it's volatile. Frequency changes are sharp and incredibly fast. And look at this. The time operators have to fix a problem shrinks from seconds all the way down to milliseconds. That just massively increases the risk of a blackout from even a small hiccup. And this isn't just a theory. As this research points out, as inertia goes down, something called the rate of change of frequency, or ROCOF, goes up. All that means is that when there's a problem, the grid's frequency doesn't just drop, it drops way, way faster. It's like falling off a ledge instead of rolling down a hill, and our traditional control systems just can't keep up. And to make matters worse, this loss of inertia isn't happening in a vacuum. It's being piled on top of other problems, like our aging infrastructure and brand new cybersecurity threats that come with digital controls. An unstable grid is also just flat out expensive. It needs more and more costly interventions to keep it balanced. And guess who pays for that in the end? We do, on our energy bills. Okay, but here's the good news. We don't have to go back to the old tech. We can actually engineer a whole new kind of stability, one that's designed for a modern grid, powered by renewables. And there are really two main paths forward here. On one side, you have battery energy storage systems, or BSS. Think of this as the fast, flexible, software-driven solution. And on the other side, you have pumped hydro storage, or PHS. This is the tried-and-true hardware-based solution that gives us back the real physical inertia that we're losing. Okay, so let's unpack this new term, virtual inertia. Instead of relying on a giant spinning piece of metal, this is all about smart software. It's a clever control function built into the inverters of a battery system. They're constantly watching the grid's frequency, and if they see it start to drop, they are programmed to instantly fire a burst of power onto the grid. They perfectly mimic what a traditional generator does, but with zero moving parts. It's pretty amazing. Now, what this chart shows is the real magic. A traditional generator's response is mechanical. It physically has to react, and that takes several seconds. A battery system providing virtual inertia, it's all electronic. It can respond in less than a second. We're often talking milliseconds. That kind of speed is an absolute game changer. It opens up a whole new, much faster way to control the grid. And then we have the other key solution, pumped hydro. The easiest way to picture it is as a giant, rechargeable water battery. You use cheap electricity to pump water up to a high reservoir, and when you need power, you let it flow back down through turbines. The huge advantage here is that those large spinning turbines give you 2 for 1. You get energy storage, and you get that good old-fashioned physical inertia that helps keep the grid stable. Now, when we compare the two, you see a really clear trade-off that is absolutely critical for anyone doing long-term planning. Batteries are incredibly fast, they're flexible, but they have a lifespan of maybe 10 to 20 years, and they do degrade over time. Pumped hydro, on the other hand, is a massive infrastructure project, no doubt, but it's built on proven, heavy-duty mechanical parts that can last for a century, maybe even longer. So, with these solutions in mind, let's get to the bottom line, an action plan. Because tackling this inertia problem isn't just a technical puzzle for engineers anymore, it's a strategic and economic must-do for every single decision maker in the energy sector. And let's be clear, the cost of doing nothing is huge. We'd be looking at a much higher risk of expensive, crippling blackouts. We could even be forced to put the brakes on new renewable projects, which would be a disaster for our climate goals. And on a day-to-day basis, keeping a fragile grid balanced just costs more money, and those costs always trickle down to consumers. So here it is, a clear 3-step plan. Step 1, the immediate priority. We have to update our market rules. We need to create incentives that actually pay for the incredibly valuable service of virtual inertia and fast frequency response. Step 2, near term. We need to fund pilot projects for these advanced grid-forming batteries, especially in the parts of the grid that are most vulnerable. And step 3, for the long term, we have to do the strategic assessments for the big, long-duration solutions like pumped hydro. And that really leaves us with one final, critical question. The way we make our electricity is changing at a revolutionary pace. The challenge for all of us now is to make sure our strategy for managing the grid, for keeping it stable and secure, is evolving every bit as quickly.